Hello everyone. In this video, we are going to explore the beauty of Pascal's triangle. It is really fascinating that we can extract a huge number of patterns and formulas from this triangle, which is only formed of integers. We can even extract formulas for pi and e from this triangle, as you will see in this video. First of all, let us remember how we construct Pascal's triangle. So we start with 1. We always start with 1. And in each row, the first number is always 1, as you can see here. And the final number is also 1 as well. Now I add each number to the adjacent one and put the sum at the bottom. So 1 plus 0 is 1, and this is why all these numbers here are 1s. And we keep going. 1 plus 1 is 2. 1 plus 2 is 3, 2 plus 1 is 3, 1 plus 3 is 4, 3 plus 3 is 6, and so on. Of course, this is an infinite triangle, meaning that we can construct an infinite number of rows, as many rows as we like. Perfect. Let us start with the patterns we can extract. Let us add the elements in each row. In the first row, we only have 1, of course. In the second row, we get 1 plus 1, and that is 2. Here it is 1 plus 2 plus 1, and that is 4, and so on. Now, what do we get here? 1 is 2 to the power of 0. 2 is 2 to the power of 1. 4 is 2 to the power of 2, and so on. From the row number 0, if we add its numbers, we get 2 to the power of 0, and so on. So if we add the numbers in the nth row, the sum will be equal to 2 to the power of n. Next, let us take a look at the numbers in this diagonal. If we add any two consecutive numbers, we will end up with a square number. For example, 1 plus 3, that is 4, which is 2 squared. 3 plus 6 is 9, that is 3 squared. 6 plus 10 is 16, that is 4 squared, and so on. So we can obtain the square numbers by adding any two consecutive numbers in this diagonal. And that is the second pattern. We move on to the next pattern. Let us list all the numbers in each row next to each other. So for example, here in the first row, I only have 1. In the second row, we have 1, 1, so let us write them as 11. Here we have 121, 1331, and 14641. Let us first discuss what these numbers are. 1 is 11 to the power of 0. 11 is 11 to the 1. 121 is 11 squared. 1331, that is 11 cubed. This is 11 to the power of 4. Now for the fifth row, if I list 1, 5, 1, 0, 1, 0, 5, 1, this is not 11 to the power of 5. Once more than one-digit numbers pop up, it becomes more challenging to find the powers of 11. One of the methods that I've seen is that we start from the right to the left. If I have a one-digit number, I write it as is. So 5 is also copied as 5. Now what about 10? I copy the first digit, which is the units digit, and the 10th digit, we add it to the next units digit, so 1 plus 0 is 1. Similarly, 1 plus 5 is 6, and then we copy this one. And this is 11 to the power of 5. But honestly, I don't like this method. Why? Because, for example, in the row for n equal to 9, there are 3-digit numbers like 126 and 126 again. So it really becomes challenging to find a way in order to extract the exponents of 11 by adding digits to each other. Actually, there is something nicer. There is an easier formula which works for all powers of 11, no matter how many digits the numbers in Pascal's triangles are. What is this method? Let me show you. Let us start with this row, so we are supposed to end up with 11 to the power of 5. Let us start from right to left, and let us multiply by powers of 10. So this one is 1 times 10 to the power of 0, plus 5 is 5 times 10 to the power of 1, then 10 is 10 times 10 to the power of 2, the next 10 becomes 10 times 10 to the power of 3. The 5 becomes 5 times 10 to the power of 4. And the final one becomes 1 times 10 to the power of 5. Now let us add all these numbers. And guess what we get? We get 161051, and that is 11 to the power of 5. Again, let's do it one more time. Let us go with this raw, for example. So this is 1 times 10 to the power of 0, plus 6 times 10 to the power of 1, and so on. And yes, it is 11 to the power of 6. So as I mentioned, this is a better formula which works for all powers of 11. The next pattern is called the hockey stick pattern. Let's see what this is. If we start from anyone on the first or the last diagonal, let's go for example with this one, and we move down as much as we want. Let me stop here for example. Now let us add these numbers. We get 1 plus 4 is 5, plus 10 it's 15, and we get this. Let's do one more. Let us for example start here. 1 plus 5, that is 6, plus 15, that is 21, and here you go. Maybe one more. 1 plus 4, that is 5, plus 10, that is 15, plus 20, that is 35, and that is the 35. So as you can see, the shape that we are getting is a hockey stick-like shape, right? For any hockey stick-like shape, we construct, starting from any of these ones on the first or the last diagonal, the sum of the numbers on the shaft of the hockey is always going to be equal to the number on the blade. And this is why it's called the hockey stick pattern. The next pattern is really interesting. Let us construct the shallow diagonals and add all the numbers we cross. So here we only have 1. For the other shallow diagonal, we also have 1. In the next diagonal, we get 1 plus 1, that is 2. Let me change the color to make it less messy. So 1 plus 2 is 3. Here we get 1 plus 3 plus 1, that is a 5. Next, we get 1 plus 4 plus 3, that is an 8. 1 plus 5 plus 6 plus 1, that is a 13, and so on. Now what are these numbers? Let us list them. So we have 1, 1, 2, 3, 5, 8, 13. Let me list more. 21, 34, 55, 89, and so on. What do these numbers remind you of? That is the Fibonacci sequence. How is this sequence defined? It is defined as follows. The first two terms are ones, and the next term is just the sum of the two previous consecutive terms. So for example, 2 is 1 plus 1. 3 is 2 plus 1. 5 is 3 plus 2, and so on. And this is the general formula. So as I told you, the first two terms of the sequence are 1, and then each term is the sum of the two previous terms. So surprisingly, Fibonacci sequence can also be extracted from Pascal's triangle. The next thing I want to talk about is how to extract the so-called Catalan numbers from Pascal's triangle. But first of all, let me show you what Catalan numbers are. The nth Catalan number is represented as Cn, and it's equal to 1 over n plus 1 multiplied by the combination 2nn for n greater or equal to 0. And it's also represented as 2n factorial over this product of factorials, or as well as the product of these numbers. So this means n plus 2 over 2 multiplied by n plus 3 over 3 plus so on up to n plus n over n. It is easy to derive these formulas. By direct calculation, we can obtain this formula from this, and then we can obtain the other formula. Let me list some of these numbers. So we have 1, 1, 2, 5, 14, 42, 132, 429, and so on. And nicely, we can also extract these numbers from Pascal's triangle. To do that, let us first mark the middle vertical line we obtain. So we get 1, 2, 6, 20, 70. Let me add the next two numbers. So here we're gonna get 252, and the next one will be 924, and so on. Let me circle them. Now, if we pick any of these circled numbers and subtract the adjacent number from it, we're gonna get a Catalan number. For the first number, we get 1 minus 0 because we don't have any adjacent number, so that's 1. 2 minus 1 is 1. 6 minus 4 is 2. 20 minus 15 is 5. 70 minus 56, that's a 14. For the next, the adjacent numbers are 210 and 792. So 252 minus 210, that is a 42. That's another Catalan number. And 924 minus 792 is 132, and this is also a Catalan number. For the next pattern, let us cross all the odd numbers in this triangle. So we have all these, as well as these numbers. Then we have these, 1 and 3, another 1 and 3, 1, 3, 3, 1. We also have 1, 5, 15, and 35. Another 1, 5, 15, and 35, and this raw, and so on. Let us shade all the triangles formed by these odd numbers. What is that? This is called Cinsky Triangle. So if we keep going like that, all the shaded triangles we obtain will be equilateral triangles, no matter how we go so far. So we can magnify this triangle indefinitely, and the pattern persists. And all of these triangles, as I mentioned, are equilateral. So this is a fractal. And this is how it looks like if we keep going. So as you can see, we have an equilateral triangle here, as well as here, and so on. The next feature I want to talk about is the binomial formula. And I think almost everyone knows this pattern, that all these numbers can be expressed as combinations. So for example, this is 1, 0, and this is 1, 1. This is the combination 2, 0, that is 2, 1, and this is 2, 2, and so on. And this allows us to construct the binomial formula and extract the coefficients from the Pascal's triangle. Let us remember what the binomial formula is. So x plus y to the power of any n is this sum. So it is combination n0, x to the power of ny to the power of 0. I subtract 1 from the power of x and add it to the y. We keep going like that, and eventually x will have an exponent of 0 and y will have an exponent of n. And let us recall the combination formula. Here it is. So if we expand the formula, we're gonna get this expression. So for example, the combination n0 gives us 1, n1 gives us n, and so on. Let us do some examples and see how we can extract the coefficients from Pascal's triangle. Let us discuss these examples. For n equal to 2, the coefficients we get are 1, 2, and 1, and here they are. We can extract them from the raw of order n equal to 2. Similarly, a plus b to the power of 3 has coefficients 1, 3, 3, and 1, and here they are. From the raw of order n equal to 3, same thing for a plus b to the power of 4. I have 1, 4, 6, 4, and 1. And here they are from the raw of order n equal to 4, and so on. For the next property, I'm going to construct the Pascal's triangle, as you can see, as a right triangle. What are these? 1, 2, 3, 4, 5, 6, and so on. These are simply the natural numbers or the counting numbers. The next numbers are called the triangular numbers. What are triangular numbers? A triangular number Tn is a number that can be represented in the form of an equilateral triangle, for which each raw contains one more element than the previous one. Let me explain what I'm talking about. So this is the first triangular number. So T1 is equal to 1. That's the second. T2 is equal to 3. This is the third. T3 is equal to 6, and so on. For the first triangular number, T1 is equal to 1. Let us represent it by 1 dot, because we have 1. For the second triangular number, we have 3. So we copy the first dot and add another row which contains 2 dots. So the next row contains one more dot than the previous one, and we end up with 3 dots in total, and an equilateral triangle is formed. Same for the next triangular number, T3 is equal to 6. So we copy the previous triangle and we add a new row which contains 3 dots. This means 1 dot more than the previous one, and this is another equilateral triangle, and so on. So the next triangular number will contain 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and yes, T4 is equal to 10. Now, is there a general formula for these numbers? The answer is yes. The formula for the nth triangular number is n into n plus 1 over 2 factorial, which is equal to 2, but I'm going to keep it as 2 factorial because later on I want to show you another pattern. What about the next column? These are called tetrahedral numbers. Let's represent them by small tn. So this is little t1, this is little t2, and so on. Now, what are tetrahedral numbers? Again, as we define triangular numbers, a tetrahedral number is a number that can be represented by a tetrahedron. What is a tetrahedron? That is a pyramid with a triangular base. So that's what we call a tetrahedron. And by the way, the nth tetrahedral number is the sum of the first n triangular numbers. For example, 4 is 1 plus 3. 10 is 6 plus 3 plus 1, and so on. Let me show you how these tetrahedral numbers look like geometrically. So T1 is 1, that's only 1 dot. T2 is equal to 4, which means 1 plus 3. So we have 1, and we have another 3 here, and we end up with a tetrahedron. Let us do one more. T3 is equal to 10, which is 1 plus 3 plus 6. So here we have 1, 1, 2, and 3. That is an equilateral triangle. Then 1, 2, and 3, 4, and 5, and 6. That is the next equilateral triangle. If we join all of them, I will end up with what? I will end up with a tetrahedron, and so on. There is also a general formula to derive all the tetrahedral numbers as we explained in the triangular numbers. So the nth tetrahedral number is n into n plus 1 multiplied by n plus 2 divided by 3 factorial. If you remember, the triangular number formula was n into n plus 1 over 2 factorial. So now we add n plus 2, we add another factor, and the 2 factorial becomes 3 factorial. Now, is that all? Not really. Why? Because the next column represents the so-called pentatope numbers. Let me call them Pn. So what is a pentatope? Well, we can think of it as a 4-dimensional tetrahedron. Of course, it's not possible to visualize it. So as you may have noticed, we started with triangular numbers. These are 2-dimensional figures. Then we moved to tetrahedral numbers, and these are 3-dimensional figures. Now for the pentatope numbers, these are 4-dimensional figures, or we can call them 4-dimensional simplexes. And we keep going like that. So these are 5-dimensional simplexes. These numbers represent 6-dimensional simplexes, and it keeps going on. Moreover, for every type of these numbers, there is also a general formula. So for example, for pentatopes, Pn, all we have to do is replace Tn by Pn, and I think you've guessed it, we have to add n plus 3 here, and the denominator becomes what? It becomes 4 factorial. Same thing happens for 5-dimensional simplexes, and so on. And we can finally derive a general formula for any nth dimensional simplex number, and this is it. As you can see, it's the combination d plus n minus 1 over d. Of course, d stands for the dimension. There are 2 more things I want to talk about regarding the formulas and patterns we can extract from the Pascal's triangle. I would like to talk about the number pi and then the number e. Well, how can we extract a formula which represents the number pi from Pascal's triangle? First of all, let me show you the formula. The formula is Pi minus 2 is 1 over 1 plus 1 over 3 minus 1 over 6 minus 1 over 10 and so on. So we keep alternating the signs 2 by 2. I mean we have plus plus, minus minus, plus plus, minus minus and so on. And what are these numbers in the denominators? If we take a look at Pascal's triangle, let us look at the third diagonal. So the first denominator is 1, the second denominator is 3, the third denominator is 6, and so on. So these terms are just the reciprocals of the numbers in this diagonal. And by the way, we can write all these numbers as combinations. So 1 is 2 combination 2, 3 is 3 combination 2, and so on. But I will also like to show you the proof of this formula. So let us start. I will start the proof by using the Leibniz formula for pi, and this is it. It's pi over 4 is equal to this sum. Let us first move the 4 here so we get this expression. We expand the series so we get 4 into 1 over 1 minus 1 over 3 and so on. We then distribute the 4, and I'm going to write this 4 over 1, which is 4, as 2 plus 2 over 1. So we get this expression. Then I will factor 2 from all these terms and keep the first term as 2. So this 2 becomes 1, this 4 becomes 2, and so on. Now the next step is the following. We notice that all the denominators are odd numbers. What I'm going to do now is to add and subtract fractions with even denominators. So here I will add minus half plus half. Here I will add plus 1 over 4 minus 1 over 4. Here minus 1 over 6 plus 1 over 6 and so on. And I will add all these terms in a way that the signs are alternating. So plus, minus, plus and minus, then plus and minus, and so on. One more thing I'm going to do here. I will write all these terms as fractions with numerator equal to 1. So for example, 2 over 3 is 1 over 3 and 1 over 3. Of course, this is minus 2/3, so it becomes minus 1/3 minus 1/3. This is plus 1 over 5 plus 1 over 5. And we keep going like that. And this is the expression we obtain. Next, I will put every 2 consecutive terms in parentheses. Of course, if it happens that we have minus in the first term, I have to take it out, and it becomes 1/3 minus 1 over 4, for example, and so on, and that is the expression we obtain. We notice here that in each parentheses we have a difference of 2 fractions, where the denominators are consecutive numbers, so we can benefit from the following formula. 1 over n minus 1 over n plus 1, and this exactly matches with the fractions in each parentheses. This is equal to 1 over n into n plus 1. So this is how our expression looks like now. Let us distribute the 2, and this is what we get. So now we get pi is equal to 2 plus all these fractions. All left is to do simplifications in each fraction, so these 2's are cancelled out, as well as these. Here we will get 1 and 2 is left, and so on. And we get our result. We just move the 2 to the left, and we end up with pi minus 2 is equal to the sum of all these fractions whose denominators can be extracted from Pascal's triangle. The last thing I want to talk about here in this video is how to derive a formula for the number e from Pascal's triangle. To do so, let us multiply all the numbers in each row. So for example, here we only have 1. Let me call it S0 is equal to 1. This is S1 is equal to 1 times 1, and that's 1. That is S2, that's 1 times 2 times 1, that is 2. S3 is equal to 1 times 3 times 3 times 1, that is 9, and so on. And we can write these numbers as products of combinations. So 1, for example, is 1, 0 times 1, 1. 2 is 2, 0 times 2, 1 times 2, 2. So Sn becomes what? Becomes n0 times n1 times everything, all the combinations up to the combination nn. So in general, we can write Sn as this product. Now it is obvious that as n becomes very large, Sn approaches infinity. But the nice thing is the following. If we calculate the limit of Sn minus 1 times Sn plus 1 divided by Sn squared, we're going to get E. And this is how we can derive a formula for E by just multiplying the terms in each row. And again, I would like to show you the proof of this formula. But let us first note that this fraction can be expressed as Sn plus 1 over Sn, all of it divided by Sn over Sn minus 1. So the idea of the proof is to find what this ratio and this ratio are equal to, and then find the limit of the result as n goes to infinity. Let us first start by expanding the product. So this becomes n0 times n1 times all the combinations up to nn. And these are the corresponding expressions for our combinations. Now let us notice the following. Each denominator shows up twice. So for example, we have 0 factorial n factorial, as well as n factorial times 0 factorial. Here we have 1 factorial times n minus 1 factorial, which also pops up here. So it turns out that each factorial shows up twice, which means we can write each factorial as the term squared. So it becomes 0 factorial squared times 1 factorial squared times 2 factorial squared up to n factorial squared. We also notice that all the numerators are n factorial. We started from 0 up to n, so this means we have n factorial multiplied by itself n plus 1 times, which means I can write n factorial to the power of n plus 1. So this is what we get. Let us write it in the form of a product, and that is what Sn looks like. Now we are able to calculate Sn over Sn minus 1, as well as Sn plus 1 over Sn. So this is how Sn over Sn minus 1 looks like. So all we have to do here is to replace every single n by n minus 1 in order to get Sn minus 1. We multiply this fraction by the reciprocal of this, and this is what we get. I will then expand n factorial to the power of n plus 1 like this. So we have n factorial multiplied by itself n plus 1 times. And for this, we multiply n minus 1 factorial n times by itself. Now each n factorial is n into n minus 1 factorial, that's a formula. And consequently, this n minus 1 factorial cancels with this. It happens for all these terms, but remember, here we have n plus 1 times of n. However, here we only have n times of n, which means the final factor is kept untouched. So this n factorial remains as is, and all the rest terms become n's only. So here we're left with n to the power of n. I'm talking about all these terms. We're also left with n factorial. I'm talking about this. For the bottom, everything here is cancelled out. We are only left with this. And that is what we get. Moreover, this is 0 factorial squared times 1 factorial squared up to n minus 1 factorial squared. And this is 0 factorial squared times 1 factorial squared times n minus 1 factorial squared times n factorial squared, which means everything will be cancelled and I'm left with n factorial squared. And that's what is left. We cancel this n factorial with this n factorial, and this is what we get. Similarly, Sn plus 1 over Sn will be n plus 1 to the power of n plus 1 over n plus 1 all factorial. So all left is to divide these two fractions. We get this. Let's multiply by the reciprocal of the bottom fraction. Now this is n plus 1 to the power of n times n plus 1 to the power of 1. This is n plus 1 times n factorial. This n factorial is cancelled with this n factorial. So we are left with n plus 1 to the n times n plus 1 over. Let me interchange these two terms. We can put these two terms under the same exponent of n. And we can cancel these. So we are left with n plus 1 over n. Of course, this is n over n plus 1 over n. And this is 1 plus 1 over n to the power of n. And what is the limit of this as n goes to infinity? That's a popular calculus formula. It is E. And therefore, we have proved this formula. And now we can say that the product of the rods in Pascal's triangle will in some way give us the number E. Actually, there are so many more patterns in Pascal's triangle, there is no way to put everything in one video, and I believe that later and later, we will see more patterns and more nice formulas that can be derived from this Pascal's triangle. That's all for this video. I hope you liked it. Thank you for watching, and see you soon.